So here's chapter 8, atoms and periodic properties. Basically, we're going to study, we're going to get to the periodic table and learn more about the periodic table. Alright, so we're going to find out where the model of the atom comes from. And it actually goes back to the time of the Greeks. There were some Greeks that basically, like, you just imagine a piece of, I don't know, like a meter stick, for example. Okay, so that's a good example. If you take a meter stick and you were to cut it in half, okay, here, let me wait a second. All right, so here's the meter. I think it just is easier to see this. So here's the meter stick. If you were to cut it in half, and then take one of those halves, you'll get the idea in just a second, and cut that in half, and then take one of those halves, and then cut that in half. Basically, the Greeks wondered whether you could keep doing this forever and ever and ever. Okay, and Aristotle, where were we? Here it is. Sorry, and Aristotle and Plato, who were of course very, very famous Greek natural philosophers, because they certainly weren't scientists in the modern sense. They didn't use the modern criteria of experimentation. Basically, these two, who were very, very influential, said that you could keep dividing matter infinitely. And there was another guy, Democritus, who, for no really good reason, said, no, you're going to come to some smallest chunk of matter, and that he called an atom. It turns out, of course, Democritus was right, but not for good scientific reasons. So I want you to understand that. I mean, either of these folks could have been right, but certainly back then. Now you fast forward to almost modern times, right? So the early 1800s to John Dalton, and so he brings back this atomic theory from Democritus, which kind of had been sitting in the background for a while, and there were there's a lot of chemistry going on at the time, and he looked at all the different things that were going on and basically summarized them. All right, and here were his observations, or his statements, I guess, for Dalton's atomic theory. And a lot of this is not true anymore. Of course, we made more modern discoveries. So what it says is all atoms are, or all matter is made of atoms that cannot be broken apart. Okay, indivisible atoms. That's what that means. Of course, we know that that's not true. Atoms are made of three things: protons and neutrons in the nucleus, and electrons outside of the nucleus. So we'll talk about that. So right away. But Dalton certainly didn't know that, and we can certainly excuse him for that. An element is made up of identical atoms. Well, that turns out to be not true as well. There are different isotopes of elements. For example, there's carbon-12, which is a very common form of carbon, but there's also carbon-14, which turns out to be radioactive. And they're the same atom, but they have different numbers of neutrons. So we'll get into that a little bit later. Different elements have atoms with different masses. Well, that's certainly true. That's still true. For example, oxygen is heavier than hydrogen. That was well known at the time. Chemical compounds are made of atoms in specific integer ratios. Now that's very, very important. Okay, we'll we will be using that idea throughout this chapter. Atoms are neither created nor destroyed in chemical reactions. That too is a very important observation or statement, I should say. And yeah, I mean, this is a big deal. Let's get back to this. Chemical compounds are made of atoms in specific integer ratio. So what I'm going to do with this idea of specific integer ratios is use probably the most famous molecule of them all, famous chemical compound, H2O. And the reason I start with that is, of course, everybody's heard of it. But let's examine this for just a second. What this is saying is there are two atoms. The subscript 2 here indicates that there are two atoms of hydrogen, and implied behind as a subscript of the oxygen is a 1. It's never actually written like that, but that's telling us that there is one atom of oxygen, of course. So one atom of oxygen to two atoms of hydrogen. Okay, so that's what they mean by specific integer ratios. There's integers down here. Okay, and so remember, if there, let me rewrite it, of course, properly. If there's nothing there as the subscript, as is right here for oxygen, if there's nothing actually there, it's implied that that's a 1. So whatever atom that's there, there's just one of them. Okay. All right. Very nice. So let's go back to the PowerPoint. All right. So get. And as I said, we'll get into how this original atomic theory, or well, I guess semi-original atomic theory, changed. This is certainly in the time of modern science, where we're using the scientific method. In France, there were a bunch of, and in England as well, a bunch of chemical experiments that were taking place. And as I said, Dalton basically put this forward. You fast forward about 100 years, and one of the first things that Dalton said is it turns out to be not true. J.J. Thomson, I think this is around 1897, if I remember correctly, used what are called the cathode rays. Okay, so basically this was an evacuated chamber made of glass. So vacuum technology at in the late 1800s was sufficiently good so that you could perform this experiment. Basically, through the glass there were electrical connections, and if you put a voltage across this cathode ray tube, and it had to be a sufficiently high voltage. Once you put a voltage across this, there were blue beams that people called cathode rays. Of course, later on, just to fast forward a little bit, about 50 or so years, we controlled these cathode rays with magnetic fields and drew pictures, and this eventually becomes electronically a television set. But before that, it was actually useful, and J.J. Thomson made a great discovery. By using magnets, he found that these cathode rays were charged, and they were negatively charged. Okay, and he found, in fact, that they were what he called electrons, and that is, of course, the modern. That's a very modern discovery, that atoms can be broken up into smaller chunks, certainly, and those, the first of which we call an electron. Okay, and in fact, another thing that J.J. Thomson does is he measures the charge to mass ratio of the electron. So that's going to become important to us in a little bit, because that leads to other things like, for example, what the mass of a single electron is, what the charge of a single electron is, which we already, you know, you got to remember. You got to here. Let's go back to this. Recall the charge. So what he measured was Q over m, the charge of a single electron over its mass. And, you know, we already had this in Chapter 6, that the charge of a single electron, which we know to be negative, is negative 1.6 times 10 to the minus 19th coulombs. All right, so at the time of J.J. Thomson, this was not known. This was certainly not known yet. All right, so here, let's go back to here. But we're about to figure out, you know, how that was discovered. All right, so all right. A few years later, an American scientist named Millikan performed his famous, it's called the oil droplet experiment. And basically, this is a wonderful little experiment where oil is sprayed, and basically what you want to happen is the little globules of oil will be in such a fine mist that basically one of these little globules or droplets, whatever you want to call them, pick up a single charge. And as these things fall between these two plates, which are connected to a voltage that you can vary the voltage. Basically what Millikan wanted to do is turn the voltage up to such a degree that the force of gravity would be counteracted by the electric force, and so from that he could measure the charge of a single electron, and that was actually how it was first done. The charge of an electron, of course, is negative 1.6 times 10 to the minus 19th coulombs. Okay, and so from J.J. Thomson's result, we know the charge to mass ratio. Millikan gave us the actual charge of a single electron, and then we now can figure out what the mass of a single electron is. The modern value is given right here, and you can find this in any scientific textbook. So, but that's originally where this comes from. So, you know, Dalton gave us the idea, the modern idea of atoms are indivisible; they can't be broken apart. Thomson, of course, showed that they can, and they can. And one of the parts of an atom is an electron. It has a very tiny mass. It has a very tiny charge, and it seems to be almost a point particle, where it takes up no volume. But of course, you know, and of course with Millikan's experiment, we actually measured what the charge was. We know, of course, that atoms, when you touch something, you know, you're not shocked to death when you, you know, encounter matter in normal circumstances. The matter is neutral. That is, it has just as many protons as it has electrons. And so people knew that there was something positively charged inside the atom. J.J. Thomson tried to come to the rescue by coming up with this idea of the plum pudding model, where he imagined electrons in blobs of positively charged matter, like raisins in plum pudding. He was, you know, J.J. Thomson is an English guy. The English love their plum pudding. This model turns out to be completely wrong. But of course, you know, we use the scientific method to figure out why. And I'll finish that in the next video.